Hello, and welcome back to AP Environmental Science. Today we're going to be talking about nuclear power, and nuclear power, along with hydroelectric and fossil fuels, is one of the conventional energy forms, and we do use it on a regular basis. There are, I think, 104 operating nuclear power plants here in the United States, and then there are all over Europe and in China and India, Japan. So there are all kinds of places that are relying on nuclear power. And as a matter of fact, in Dallas, we get a good portion of our power from a nuclear power plant just to the south of us that we'll talk about in a second. But the question is, what does that mean, nuclear power? What are we doing? What are the pros? What are the cons? And so that's what we're going to talk about today. Also, you'll see that this is a link. So if you look at the PowerPoint that goes with this, this is a link to a little nuclear quiz that was done by Frontline to kind of address fear issues of nuclear power, because nuclear power tends to be pretty scary for people, even though that may or may not be warranted. Okay, so first off, this is a nuclear power plant. This is 3 Mile Island, and we'll come back to 3 Mile Island in a minute. But when we think of nuclear power, this is what we think of. We think of these giant cooling towers. We've got reactor building right here, containment building right here, lots of electrical wires coming out. And so the question becomes, what's actually going on in there? So first of all, nuclear power comes from the fission of either uranium-235 or plutonium-239. And in the United States, we only use uranium-235. There's a reactor called a breeder reactor that we're not going to talk about very much that is used in France, for instance, and that uses plutonium, and we don't do that. We were going to build some in Tennessee, but we never did, and so we use pretty much exclusively one kind of reactor. But no matter what's going on, in order to have nuclear power, you have to have fission. And you take this uranium-235, you shoot it slowly with a neutron, and this slow neutron deforms the nucleus. And when it does that, it pops apart. And you get this release of energy, you get these fission products, which are highly, highly radioactive. They are nasty, nasty. You also get 3 new neutrons, which is great, because that can sustain the reaction. And so here, this neutron can start another fission here. This one can have fission here. And then these will each produce 3. And you can see where this is going. If you don't control this, it's called a chain reaction, and eventually it's going to explode, and that is a nuclear weapon. But if you can control this reaction, you can get a sustained release of energy that will allow you to generate power, right? And that's very exciting. So fission, right? Fission. Okay, now here is a general overview of what we use in the United States. They're called pressurized water reactors, PWRs. And so what we have here is uranium fuel. Now, the fuel in these fuel rods, these are the fuel rods, and this is the reactor vessel, this is the reactor itself. What we have going on here is a mix of uranium-238 and uranium-235. Natural uranium ore is a mix of uranium-238, which is not fissionable, and uranium-235, which is fissionable. Now here's the catch. In order to have a sustained reaction, you need to have 4% of your uranium as uranium-235. And then the other uranium helps absorb neutrons and all that good stuff, the 238. Natural uranium is 1%, uranium-235, and the rest of it is uranium-238. So we have to enrich the uranium. So these rods are what are called enriched uranium. They are 4% 235, and the rest is uranium-238. Okay. Oh, fun side note, when you bombard anything with neutrons, it becomes radioactive. But when you and we'll come back to that, when you bombard uranium-238 with neutrons, it decays into plutonium. So you actually get plutonium out of this uranium reactor, which is super exciting if you use plutonium as your fuel. But anyhow, so that's what's actually going to be the fuel, right, is this uranium in here. Right here are what are called control rods, and these control rods can be raised and lowered to regulate the reaction. If it starts going too fast, you can lower the control rod, slow it down. If it starts going too slow and you want to bump it up, you can raise the control rods up and, you know, give it a little bit more go. They are made of cadmium. Cadmium is a neutron absorber. Okay, it's a neutron absorber, and that's why it works to lower in here. Now, this self-contained loop is going to be filled with water. This water is going to cool down the reactor, okay? And you need that because this can get like 5,000 degrees and you don't want that. Now, having said that number, this has to be under very high pressure to keep it liquid. So this is entirely contained, it's entirely pressurized. So you've got this water flowing through, blah, blah, blah. Now, the other great thing about water is it doesn't just cool stuff off, it slows down neutrons. And in some cases, if there's enough water, it absorbs them. But here, the slowing down is important. The water moderates the reactor and keeps it going, okay? And so because it's constantly slowing these neutrons down, it's allowing more fission to occur. So we have water moderated reactors. These pressurized water reactors are also called water moderated. And so you've got this water, that's the coolant, and the moderator. We're going to come back to that later on. Now, there's a heat exchanger that is attached to a second loop. And this second loop takes heat off of this first loop, and that's great because the water in here will boil. You do not want boiling in here, no boiling, but you do want boiling in here because steam will come through and steam can turn a turbine. Running water, as you found out talking about dams, can turn a turbine to turn a magnet to generate electric current. We've talked about that. But steam can do it too. And all of the rest of the power plants that we're going to talk about, with the exception of solar, are going to make steam to turn a turbine, to turn a magnet, to generate electricity. The question becomes, how do you make the steam? And in this case, you're using nuclear fission. And so here, we've got this steam. Now, you want to condense this, right, cool it off. So you've got another heat exchanger here that's attached to a third loop. But getting back to this one. So after the water condenses, it's going to go back through, it's going to cool off the coolant, make some steam, make some electricity, yay. Now, to cool this off, you're going to have a third loop. This third loop goes to what are called cooling towers, and these cooling towers have networks of pipes to help cool off the water, and then it's pulled out of usually a lake or the ocean or a river. Most of the, well, not most, but many of the lakes that these come from are man-made, and they're actually made for the nuclear reactors, I mean, for the power plant itself. For instance, ours in Glenrose, across from Glenrose, in Granbury, our reactor is called, power plant is called Comanche Peak, and the lake that's next to Comanche Peak was made for Comanche Peak. So anyway, so this pulls it out. Now the problem is it's a little bit warmer than it was before when it goes back into the lake, and that can cause some problems with ranges of tolerance and what's dissolved in the water and stuff like that. And so that can be a little bit of an issue, but mostly it's close and it's clean. None of this water is radioactive. None of it is harmful. None of this water is radioactive. None of it is harmful. This water, on the other hand, is radioactive. Everything in this loop is radioactive because those neutrons, if you bombard something with neutrons, it will make it radioactive. So this is all bad stuff, yeah? But you've got this great energy. Okay, this is actually what the parts of the reactor look like, and each of these rods has tiny little uranium pellets that are about this big, okay? And that is what's going to, that little uranium pellet is where fusion is going to occur. And by the way, if you had a little uranium pellet about that size, that would be equivalent to about 1,700 pounds of coal, just as a side note. So really powerful. Fission, lots and lots of energy involved, and that's one of the reasons it's so exciting. This, by the way, is Comanche Peak. This is our power plant, and these are the two reactor vessels, okay? And the reactor, or sorry, containment buildings. Wow, containment buildings. The reactor vessels are inside these buildings, and they are huge. These buildings are immense. The interesting thing about these buildings is that if you have any sort of leakage, they're at a lower pressure than the outside. So if we think back to thermodynamics, if there's a leak, air will come in from the outside instead of going out from the inside, containing any radiation at all whatsoever. And that's really great because accidents can happen, and we'll talk about those. All right, this is the turbine. And here's another picture of the turbines. This is the steam pipe that's going to turn the turbine to turn the magnets to make the electricity. This is all still Comanche Peak, by the way. Okay. This is Comanche Peak, right there. Oh, but Texas only has 2 nuclear reactors, and there are very few nuclear reactors in the West. Now, when you look at the East, there are lots of nuclear reactors. 2 reasons. One, they started building them in the east first, and two, there's a higher population density. Now, as people started moving out west and there needed to be more electricity, nuclear power plants became popular. However, towards the end of the 70s, and there was an accident here in the United States that caused zero damage and released zero radiation, but it scared people. And so at the late 70s, early 80s, we stopped building nuclear power plants because people were afraid of them. And sometimes that fear is warranted, but for the most part, they're pretty safe, actually. On regular, day-to-day basis, nuclear power plants are very safe. But by the same token, we haven't built any since then, although there are some plans to build some new nuclear power plants, but they're very, very expensive. They're expensive to build, they're expensive to decommission, and so the question becomes, is it worth it to put the billion, or so dollars into the plant? Or not. And so there's not a good answer to that. Some people think we should, some people think we shouldn't. You'll figure out what you think. Okay, so here's your question. Which of the following is true about nuclear power generation in the U.S.? The number of new nuclear facilities coming online reached peak in 1973. There are plans to double the number of nuclear reactors. There are 103 new facilities being built right now, and the U.S. Energy Information Agency predicts increased nuclear generation by 2019, or all of the above. The only one that's true is number one. Okay, there was a peak of online or facilities coming online in the early 70s, and that tapered off as people started to fear them. And then when we had our little accident, which we'll talk about, that was it. Right? There are no plans to double the number of nuclear reactors. There are no new reactors being built as of this moment, 2012. There are about 104 working in the United States right now, but they were built in the 70s. We will have increased nuclear generation, but it won't be by 2019 because it can take a decade to build a nuclear power plant. It's very important the construction is correct. It's complicated. There's a lot of engineering, and so we couldn't actually increase nuclear generation within the next few years. Anyway, okay. Now here's the great thing though. It's what we call clean energy. There are no nitrates, no sulfur oxides, no carbon dioxide, no other pollutants, no heavy metals like the mercury that you see in coal, no volatile hydrocarbons that you get from all fossil fuels. It's clean, clean, clean. No atmospheric pollution. Okay. Now, is that really true? Is it misleading to state that because nuclear power plants use uranium as a power source instead of fossil fuels that there's no CO2 emissions produced? Yeah. Is that misleading? Yes, because fossil fuels are used in mining, transportation, and processing of uranium, or no, because nuclear reactors don't produce CO2. Well, uranium is a rock, is part of a ore, right, which is a rock, and you have to mine it, you have to transport it, and you have to take the uranium out. And we already talked about the fact that you have to enrich the uranium to make it work in a nuclear power plant. So you still use fossil fuels, but coal also has to be mined and transported and processed. So you are still saving CO2 emissions because all of these things, oil has to be drilled and processed and transported. So all of these other fuels still have the same issues with the upfront portion, but nuclear reactors don't produce more CO2, unlike fossil fuels, which burning those does. Okay, now, the really big problem, though, is nuclear waste. So nuclear is not perfect. It has lots of radioactive waste that you have to deal with. And there are actually two kinds of waste that are regulated, and that's low-level waste, which is the usual stuff, medical stuff, laboratory stuff, any sort of protective clothing or cleanup gear, some of the reactor equipment and tools, things like that. These are all, they're contaminated or they've become radioactive through neutron exposure, but these are things that are not super, super radioactive. High-level waste, on the other hand, is what you produce in a nuclear power plant, and that's going to include the spent reactor fuels they're spent reactor fuel, those rods, those spent rods that were inside the reactor. Those are super, super radioactive. They are super hot. And the only way that they become safe is through radioactive decay. And the half-life on uranium and plutonium are in the millions of years. So they're going to be radioactive for millions of years. Remember, half-life is how long it takes for half of the sample to decay. So even after, say, if you've got a half-life of 1,000,000 years, after 1,000,000 years, half of your stuff is still radioactive. Okay? And we produce 3,000 tons per year of this high-level waste. And that's probably not great. Okay, now, all of this waste, and anything you do with nuclear stuff has to be regulated. And that's going to include disposal, storage, and transportation of waste. And then other regulated activities include the actual, generation of power, all that good stuff. Who does it? The Nuclear Regulatory Commission. They're the ones who actually formulate all of the policies and regulations. They give licenses, they revoke licenses for anybody who wants to do anything nuclear. And any time that there's a legal issue, they're the ones that are going to be handling it. They also are the ones who come and investigate if anything goes wrong. And actually the FBI is also called, just in case it wasn't an accident. But the NRC is going to handle all this stuff. All right, and this is just, when you talk about radioactive waste, there are different things you have to do with this. Most of this is going to be low-level waste here, but it comes in 3 forms. There's liquid. You can also have solid, but you would like to solidify liquid to hold it in a drum or bury it or something like that. Here's the solid, and then here's the gaseous, and then this just gives you an idea of kind of what you do with it over time. It's a little flow chart for you, but the point of this slide is this. It takes a lot to actually store radioactive waste, and this is for low-level waste. For high-level waste, there's a whole different set of rules, and it's governed by the Nuclear Waste Policy Act. This is your legislation that you need to know. The NWPA says that it's the government's responsibility to provide a disposal site for the high-level radioactive waste that we have been talking about. Everything else is managed by, is overseen by the NRC, but it's managed by whoever's using it. That could be private or governmental. But high level, the government is responsible for that. And they started to build a permanent storage site that would store a lot of this stuff called Yucca Mountain. And Yucca Mountain is an area in Nevada that was used for nuclear testing, so it's already got all kinds of crazy radioactive things going on. The cool thing is it's not volcanic anymore, which is good, it makes it stable, but it used to be, and so it's made of a volcanic rock called tuff, and that tuff does a great job at absorbing radioactivity. And so it's a really good location. It's also really stable. There is a problem, though, when they did the original mapping and the USGS did the survey and all that good stuff. There was a little bit of confusion about exactly how groundwater was flowing there. And so at first they thought it would be perfectly safe with 0 groundwater contamination because it was going to be about 1,000 feet above the water table, because the water table is very deep there. And then it would be about 1,000 feet below the surface, so it would protect any surface water. But there seems to be some issues with that, and so Yucca Mountain has actually been put on hold because you do not want to spend about $60 billion to build something that you can't use. So they're doing some more investigations, but hopefully they'll get it, because that stuff in there would be radioactive, as radioactive it is right now, for the next 10,000 years or more. And this is what it would have looked like. Here's Yucca Mountain. There's the facility right inside. You'd put all this stuff in there in these tunnels, and then here's the distances to the water. Okay, so since we don't have Yucca Mountain, where does spent fuel go? About 3/4 of it is actually stored on site in pools. Right, these pools here. You can put low-level radiation or low-level waste in these what are called dry casks. This is all solid. It's been solidified if it was liquid, and you just store it in here, and it's gonna contain the radioactivity. But high-level waste is gonna have to be stored underwater, because remember, water slows down neutrons. It absorbs radiation, and if you have enough water, it'll actually block the neutrons from coming out, and that's very exciting. These are usually on site, right, these big containment pools, and even if we had a permanent facility, and we have a couple of places that they store that are specifically for this, but they're all these containment pools. Even if we were to transport it, you'd still have to wait 6 months to a year from the time that it came out of the reactor just to get it to a point where it could be transported, because it's nasty when it comes out of the reactor. Okay, now the other problem is not just the spent fuel rods and stuff like that. It's also going to be the waste from the actual mining process. You have to extract the uranium or thorium thorium is used in medical stuff for like radiation therapy, things like that, from their ores. And when you do that, there's radium that's left behind in this ore, and radium is also very radioactive. It's the stuff that they used to paint on glow-in-the-dark watches in World War II, and it gave all of the women who were working in those factories cancer. It's very famous. But anyway, so that's radium. Radium, it decays, but it decays into radon, which is also radioactive. It's a radioactive gas that we're going to talk about later in the year. So this is a big hot mess right here. There are 19 disposal sites for tailings. The problem is that at least 13 of them are actively leaking radioactive stuff into the water surrounding them. And probably the biggest culprit of that is going to be the Atlas site in Moab, Utah. And this is just a picture of it, but lots of groundwater contamination there. So this is a big problem, actually. And we've got accidents. There was 3 Mile Island in 1979. There was Chernobyl in 1986, and Fukushima in 2011, which you're probably familiar with. This is 3 Mile Island. In 1979, they had a little mishap, and the reactor lost its coolant, right? And remember, that water in the reactor is highly, highly pressurized. So when you lose the coolant, it vaporizes, and you're in danger of an explosion. Fortunately, they caught it. There was no explosion. There was no radioactive release, but it scared people. Now, if you don't catch it, then this can happen. This is Chernobyl. This was 1986. And this is reactor number 4. Now, the Chernobyl reactor is different than the U.S. reactors. This is an old Soviet reactor. And the Soviets didn't use water moderated. They used what are called graphite moderated. And graphite moderated reactors have water for a coolant, but they have graphite blocks for the moderator. So the problem is, if you lose the coolant, you don't lose the moderator. In U.S. reactors, you lose the coolant, you lose the moderator. That slows the reaction down, and it's easier to stop. In the graphite reactors, the reaction actually speeds up, and you've got no coolant, and so the core melts down, the water vaporizes, and it explodes. You get this massive steam explosion. This was caused by steam. Everything that you're looking at is entirely radioactive. It's all radioactive here. The fires in this building burned. This happened in April. They burned through like mid-May. And then people actually had to come in and kind of consolidate all this debris and bring it back into the building so they could build this, what's called the sarcophagus. The sarcophagus is a huge concrete containment building. Because concrete, if it's 12 feet thick or thicker, will actually contain gamma radiation, which is what all of this is going to be. That's the high level, bad for you, really bad for you radiation. But anyway, so this, sadly, people did this because they sent in robots to do it, like little tracked robots with arms. But the radiation was so great that it actually fried all the circuits, so they couldn't do it. So they actually sent in the Russian army, and they didn't tell them the amount of exposure that they were having, and lots of them died later. And in the first 2 weeks, they had to stop the fires, and so they had firemen flying over in helicopters, dumping neutron absorbers and fire suppressants. And because there was this radiation just coming off the top of the building, there was this massive radioactive plume that was released in the explosion. The majority of the firefighters also died. And so this was a huge, huge tragedy, highly preventable, actually, because it was due to human error, but really sad. And a lot of people, we learned a lot of lessons from this. And it's still actually really radioactive, and the area surrounding it is the town that's near it is still abandoned, actually. Now, this is Fukushima. This was not human error. This was about the earthquake. When the earthquake happened, and when earthquakes happen, or other disasters, when the electricity shuts down, you have danger there of not having the electricity to run the safety systems, and the reaction can get out of control, and other things can happen. And so Fukushima actually exploded, and this is the result of the explosion. It's not a nuclear explosion, but it's all still radioactive and still bad. Okay. So which of the following is not a significant environmental or health issue associated with nuclear power? It produces greenhouse gases and atmospheric pollution, causes local thermal pollution, it produces radioactive waste, human accidents and carelessness can expose people to radioactive activity, or it's difficult to determine who's doing what with their nuclear stuff. Well, it does not produce greenhouse gases or atmospheric pollution. It does produce the local thermal pollution in the lake, river, or ocean that is pulling, that is the source for the third coolant loop. We already know that there's radioactive waste. And Chernobyl was caused by carelessness. And accidents can happen. There are other accidents that we're not going to talk about. But for the most part, they're pretty safe. Now, an issue that we're actually not going to talk about, because it's not really an environmental science issue, but I do want to point it out, that it's really hard to know what people are doing with nuclear stuff, because the same processes that enrich fuel for power plants also enrich fuel for nuclear weapons, and that's a really scary thing. And there are nations that would use nuclear weapons pretty much without hesitation, and that's a big issue. It's a foreign security issue. It's a global issue. So, okay, now there's another way that's really clean to make energy, well, to produce energy, and that is fusion. So if fission is splitting an atom, fusion is smushing two of them together, and they're little. Fission is really big atoms, fusion is really little atoms. It's really clean. It produces helium and some neutrons that can be absorbed. It's really great. It produces far more energy than fission does. So the question is, why don't we do it? It's really hard. You have to put in more energy right now to make it happen than the energy you get out of it. At least we do. Now, stars, they do that all the time. That's why they glow. So there's fusion going on all over the universe. But for people to do it, it's a really hard thing, and it's very energy expensive. But basically, you have two hydrogen isotopes. You smush them together. You release tons of energy. You get helium and a little neutron. And it's super exciting. It has a lot of potential if we can get it to where we can do it for less energy than we're using now. But here's two ways that you do it. One is magnetic confinement. These are giant magnets, and they accelerate this gas until it's plasma, and then the plasma gets hot enough, like millions of degrees, to smush the hydrogen together. This is obviously a drawing, by the way, but this is, what happens inside. The other thing that you can do is, and these are people, by the way, shoot hydrogen isotopes with giant lasers and get enough energy to smush them together to release energy. And again, it's kind of you put as much into it as you get out of it right now. But if we could do it for less, this would be a great source, because it is actually really clean. No radioactivity at all, and that's great. Here's a fun picture of that machine running, which is exciting, and there's a discharge of static electricity when this happens, and this is lightning across the surface of the water. This is important to the class in no way at all whatsoever, but it's awesome. So there's your picture of that. Now, the other downside of fusion is that we actually do use it now. We don't use it to produce electricity. We, once again, use it to do some other things. But let's talk really quickly about reactors. If they could be built successfully, which of the following would not be one of their advantages? Little risk from terrorism, no carbon dioxide emissions, low cost of operations, or lower levels of radioactive waste. Well, it's, you could blow something up, but you're not going to have the radioactive stuff, so it's not a huge terrorist target. No carbon dioxide emissions. If you think power plants are expensive now, fusion reactors would be crazy expensive. So this is going to be high cost of operation. But there's not radioactive waste produced, and well, there's a minimal amount because those neutrons, but it's really small. Now, what we do with them with fusion now is we make the H-bomb. The H stands for hydrogen. It is a fusion bomb. It is set off and produces much more power, but you have conventional explosion, atomic explosion to make the hydrogen explosion. This is really complicated. But these ships are 5 miles apart from each other, just so you know. This ship right here is 5 miles from that ship. That is a big explosion. We've never detonated one above water. This was a test of one of the first H-bombs, which was, it's a fusion bomb. It's lots and lots of energy. So we do use it. We just don't use it for anything constructive. All right, if you have any questions about nuclear power, please make sure that you ask next time, and I will see you later.